All right, we are going to wrap up Unit 6 today, and we're going to do that by looking at one more theorem, and it's the fundamental theorem of algebra. And then we're going to kind of practice putting things together and using some of the theorems from the last unit and some of the last lesson and some of the topics that we've covered in this unit as a whole. So first of all, just some fun little facts, history facts. The fundamental theorem of algebra was given by Carl Friedrich Gauss. He was a mathematician who proved that all polynomial equations can be solved by using complex numbers. So there's not a single polynomial equation that's actually unsolvable, like we've been led to believe up till now. We looked in Unit 5 at how to solve problems because of imaginary numbers, and that means that when we start incorporating imaginary numbers, we can solve any polynomial that's given to us. And so he discovered the fundamental theorem of algebra. And the fundamental theorem of algebra says this: if p of x, or a polynomial, is a polynomial of degree n greater than equal to 1 with complex coefficients, then p of x equals 0 has at least one complex root. That's a lot of words. Not 100% sure what that means, maybe? Well, let's put it into some other words. If a polynomial has degree n, it has n roots. And this is something that we've already been talking about. If we have x to the third power and then a bunch of other stuff following it, it has 3 roots, or 3 solutions, 3 x values. The highest degree tells us how many answers we should have, even if some of those answers are repeating, and that's where we looked at the multiplicity. So, find the number of complex roots, the number of possible real roots, and the possible rational roots. So by the fundamental theorem of algebra, how many complex roots are there? So by that theorem that we just talked about, how many total solutions are we going to have to this problem? Because the highest degree is 3, we are going to have 3 roots. We are going to have 3 solutions. Now, in the last lesson, we looked at the imaginary root theorem. And so we want to know how many imaginary roots are there. Well, think about it this way. I can have, if I have I, what other root do I also have? I also have negative I. If I have 2 plus I, what else do I have? I have 2 minus I. They always come in pairs. If I have I have to have negative I as well. They're always going to go together. So that means that the number of imaginary roots that I can have is always going to be either 0 or an even number. So for this question here, I would say that I can have 0 or I can have 2. I cannot have 4 though. Why can I not have 4 imaginary roots? I can't have 4 imaginary roots because my highest degree is 3. So I know I've got 3 solutions. If I said 4, that would be more solutions than I can actually have. So I can have 0 or I can have 2, but that's it. And then finally, by the rational root theorem, what are the possible rational roots? So this is the one that we looked at with the values of p and q. So what are your values of p and q here? P is equal to 6 because it's the last number, and q is equal to 1. So when I write p over q, I'm going to put all the factors, and I have to write them as positive and negative. So I could have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, and plus or minus 6 over 1. Oh, I don't know how that's a 6, but that's okay. 6 over 1. There we go. So those would be all of my imaginary roots, and you could rewrite that to say plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Any of that would work. So we are going to find all the zeros of the polynomial, and now we're just going to kind of have those theorems tucked into the back of our brain to say, okay, I know that there are 3 solutions because my degree is 3. You just applied the fundamental theorem of algebra if you thought through that. And what we're going to do is use the rational root theorem, I just lost my words for a second, to figure out what are our possible starting rational roots. So I'm going to find my p and my q values, which this would be q, this would be p. So when I do my factors for p over q, I'm going to get plus or minus 2 over 1, plus or minus 1 over 1. So I have 4 values that I can test. 2, -2, 1, -1. I am going to pick a value to start with. I'm going to start with -1. And so here's the downside. Remember we did this in the last lesson where we just had to test until we found one of these that worked. But I promise one will work. So we've got -1. So I've got 1, 1, -1, and 2. Doing synthetic division would give me 1, -1, 0, 0, -1. That would give me +1. That's not going to give me a remainder of 0. So let me try another one. I'll try +1 this time. All right, so that gives me 1, 1, 2, 2, 1. Okay, that doesn't work. What if I try -2? Just working my way from right to left. And again, it doesn't matter what order you try these in. There's no rhyme or reason. It's not like, oh, well, 1 didn't work last time, so it will this time. Unfortunately, it's just purely guess and check. So we get 1, -2. This would give me -1, +2. That would give me 1, -2. Hey, there we go. Got a remainder of 0. So that means that one of my zeros is positive, or is -2, excuse me. I plugged in -2. Now, when I write my polynomial, I get x squared minus x plus 1 equals 0. And I cannot factor this because I'd be looking for 2 numbers that multiply to 1 and add to 1, and none exist. So I am going to use a quadratic formula. So I get x equals -b. So a is, let's do this, a is 1, b is -1, and c is +1. So I'm going to get -1 plus or minus square root of b squared minus 4ac all over 2 times a. So this is going to give me 1 plus or minus 1 minus 4 all over 2. Well, 1 minus 4 would give me -3. The only thing I can do to simplify that is to move an I outside so that it's not a negative under the radical. And so I get 1 plus or minus I radical 3 over 2. And this would be my other 2 answers. It was a complex number, and notice that I have 2 solutions, the positive and the negative. So I'd get 1 plus or minus I radical 3 over 2. And that would be all of the zeros of the polynomial. By the fundamental theorem, I should have 3. I've got 1, 2, 3. We're doing something right. All right, so start off by making a list of the possible rational roots for this polynomial. Here's our list of the possible zeros for the polynomial. Plus or minus 8 over 1, plus or minus 4 over 1, 2 over 1, and 1 over 1. Now I want to point something out. Up till now, we've mostly been looking at examples where the first term, or the leading coefficient, is equal to 1. If this was a 2, let's just say hypothetically, then I would also have to go through and put each of these numbers over 2 and say plus or minus 8 over 2, plus or minus 4 over 2, plus or minus 2 over 2, and plus or minus 1 over 2. And then I could simplify from there and say, like, oh, that 4 happens twice, so I don't need to write it twice. I would just say that positive -4 is a possible solution. And then 2, 1, and then 1/2. It is possible to have a 1/2. And so it's just really kind of tricky, I think, to have a 1/2 in that backwards L where you're having to multiply it, but it is possible. So I just wanted you to see that that is a thing. But I've been mostly focusing where the leading coefficient is 1. All right, so I'm going to start testing values. I think this time I'll start from the right. Yeah, we'll start from the right again. So we'll do 1. I just like using the smaller numbers. We'll see what happens. So I get 1, 1, -1. So this would be -1, 3. That's not going to be right. So that's not it. -1 would give me, oops, 1, -2, 4, -8. So 1, -1, -3, positive 3, 7, negative 7. All right, so there I've tried one, I've tried negative 1. You try some others and see which one of these works for our solution. If you plug in 2, you would get 1, negative 2, 4, and negative 8. So 0, 4, 8, and this would be our real root. So we would have x equals 2. If I write my polynomial, I'd get x squared, x squared plus 4 equals 0. And then when I go to solve that, what would be the final two zeros of the polynomial? I could use the square root method because I don't have an x term. I have an x squared, but not just x. So I could subtract 4 to both sides. X squared equals negative 4, square root, x would equal plus or minus 2i. So my other answers would be plus or minus 2i. And I have all three solutions that I was told that I needed. So really the only new thing that I introduced today was the fundamental theorem of algebra, but it's really not even that new because we've already been talking about how to figure out, do I have enough solutions? I hope that if anything that this just kind of reinforced in your mind how to kind of work with the P and the Q using that rational root theorem and how to test for possible solutions. Let me know if you have any questions and I'd be happy to help.